Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. In the previous modules of magnetostatics, we have discussed a vector phenomenon called magnetic field intensity, which is represented by H, and we have seen that it is pretty much similar to the electric field intensity E bar. And we have also seen an Ampere circuit law, which, as mentioned, can be used to determine the magnetic field intensity for some special cases. The special cases being the symmetry existing. You may remember that this discussion is pretty parallel to the discussion we had in electrostatics, where we have used Gauss law to determine D and E. In this module, we define a vector phenomenon called magnetic flux density, which is pretty much similar to the electric flux density. Where the electric flux density was the number of electric field lines passing through unit surface area, the magnetic flux density is the number of magnetic flux lines passing through the unit surface area. So if you want to determine the magnetic flux lines, you can use the surface integral to the magnetic flux density and get the magnetic flux lines. And the magnetic flux lines are also imaginary lines which convey the direction of magnetic fields like the electric flux lines. Whereas an electric flux line originate at a positive charge and terminate at a negative charge, magnetic flux line originate at a north pole and terminate at a south pole. So consider a closed surface, then the net number of magnetic flux lines leaving the surface is equal to the number of north poles inside the closed surface. This pretty much looks like the Gauss's law. That is, if you have a closed body and you have 5 north poles inside that, then 5 flux lines would be leaving the body. Similarly, if you have a closed surface and there are 15 south poles inside, then the 15 flux lines would be entering the body. But in actuality, magnetic monopole can't exist. Because magnetic monopole can't exist, any body which you take would always be magnetically neutral. As many north poles are there, those many south poles are there. So the number of flux lines originate and terminate at the same body, inside the same body. Hence, no flux lines leave or enter a closed surface body. So I can write that the closed surface integral of magnetic flux density is always equals to 0. So this is pretty much similar to the electric flux density is Gauss's law. The only difference being the magnetic charge enclosed is always equals to 0 for all bodies, right? So because the closed surface integral is 0, by applying divergence theorem, I can say that the volume integral of divergence of B is also equals to 0, and this should hold for all the bodies. Hence, I can write that the divergence of magnetic flux density is always equals to 0. This is the final Maxwell's equation for static fields. We combine all these equations and have a special discussion on the Maxwell's equations in the next section. But right now, I can say that this is the final Maxwell's equation for static fields. We have already seen that there was a relationship between the electric flux density and the electric field intensity. The electric flux density is a medium independent. It is independent of medium, whereas the electric field intensity is dependent on medium. This is independent on medium. This is dependent on medium. Now, a similar relation exists between B bar and H bar, that B bar equals to mu H bar. But the interesting thing here, the difference is H bar, as we have seen, is not dependent on medium. The magnetic field intensity is not dependent on the medium, whereas the magnetic flux density is dependent on the medium. The scalar mu is called the permeability of the medium. It is the ability of the medium to allow the magnetic flux lines to pass through it. That is a small relationship between the electric fields relation and the magnetic fields relation. Let us discuss something called Helmholtz theorem, which is a vector algebra concept. I have gone back to discuss vector algebra to specify a particular interesting point. Any vector field can be expressed as, Helmholtz says that any vector field can be expressed as sum of gradient of a scalar field and curl of a vector field. If you consider any vector field V bar, this can be written as gradient of some scalar field plus curl of another vector field. This is Helmholtz theorem, and this is applicable for all the vectors. Whatever may be the vector, you may write. In such case, this S is called the scalar potential of V bar, and this A bar is called the vector potential of V bar. If we consider an irrotational vector field, an irrotational vector field is a vector field whose curl is 0 at all points. That is, del cross I bar is equals to 0. If you have a vector field whose curl is 0 at all points, then such vector fields are called irrotational vector fields. You may remember from the conservative property of electric fields, we have got that del cross E bar is equals to 0. Therefore, this E bar, the electric field intensity, is an irrotational vector field. Now, for such cases, any vector field can be expressed purely as gradient of a scalar field, because curl of gradient is always 0. Because this curl is 0, that means this vector field must have been formed as gradient of some scalar field. So this is following from this rule that curl of gradient of a scalar field is always 0. Because curl of gradient of a scalar field is always 0, if you have a vector field whose curl is always 0, that means that vector field must have been gradient of some scalar field. And such scalar field is called the scalar potential of the vector field, and that vector field will not have any additional vector potential. So electric field intensity due to static charges, as we have seen, is irrotational, then del cross E bar is equals to 0. Therefore, E bar can always be expressed as gradient of a scalar field which was given the name electric potential. Right? Similarly, if the vector field is a solenoidal vector field, the meaning of solenoidal vector field is a vector field whose divergence is always 0. One such example which we have seen already is the magnetic field intensity, magnetic flux density. As we have seen, del bar dot B bar is always equals to 0 because magnetic monopoles won't exist. Because magnetic monopoles won't exist, the divergence of magnetic flux density is always 0. Therefore, this is called a solenoidal vector field. Now, if you have a solenoidal vector field, such solenoidal vector fields can be expressed purely as curl of another vector field. The reason behind this is divergence of curl of a vector field is always 0. Because divergence of curl of a vector field is always 0, if you have a vector field whose divergence is always 0, that means that vector field must have been curl of another vector field. I am repeating the point. Because the divergence of curl of vector field is always 0. If you have a vector field whose divergence is always 0, that means this vector field must have been a curl of another vector field. This vector field would be the vector potential of the first vector field. Right? So let me erase this ink over this. Magnetic flux density, because the divergence of magnetic flux density is always 0, that means B bar can always be written as a curl of a vector field. B bar is equals to del cross A bar. This A bar is called the vector magnetic potential. Thus, some discussion on vector magnetic potential says, yes, I have told you that B bar can always be written as curl of a vector field, right? But this vector field is not unique because we have already seen that curl of gradient of a scalar field is equals to 0, right? So because of this, what happens is, if I define a new vector potential, a bar dash, a bar prime, this a bar prime, if it is written as a bar plus some gradient of a scalar field, if I calculate its curl of a bar prime would be equals to curl of a bar plus curl of gradient of scalar field. But because the curl of gradient of the scalar field is always 0, because curl of gradient is always 0, as we have seen in the previous slide, This curl of A prime is always equals to curl of A bar. This curl of A bar is nothing but B bar. So the vector potential is not unique. Whereas the scalar potential was unique, this vector potential was not unique. You may remember this expression, you may remember this logic as we may use in solving many problems of EMT. So now, after discussing the magnetic flux density and magnetic field intensity, similar to what we have done in case of electric field intensity and electric flux density, we have discussed something called as boundary conditions. Here also, we will discuss the boundary conditions. The boundary conditions are nothing but the relationship between magnetic fields of different materials which are joined by an interface. Right? Why do you have to discuss this here? Because similar to this case of electrostatics, we may have a wire carrying current because of this magnetic field might be produced. But after some distance, the material might have changed. Again, now because of this, the magnetic field intensity inside this would not be same as the magnetic field intensity inside medium 1. But using the formula, using the concepts which we have discussed till now, we may try and establish a relationship between this H1 and this H2, and this study is named boundary conditions. Right? So let us move on. If you have a medium 1 and you have a magnetic field intensity, this can be decomposed into two components, the tangential component and the normal component, similar to what we have seen in the earlier discussion. Right? So one thing, a component which is not along the normal to the surface is called the normal component, and the component which is perpendicular to the normal component and is lying along the surface is called the tangential component. So if you have a medium 1 and medium 2, and this is the normal which I consider, and this is the magnetic field intensity in medium 1, and this is the magnetic field intensity in medium 2. Again, the angle in the medium 1 to the normal is theta 1, and the angle with medium 2 with normal in medium 2 is theta 2. This is pretty much similar to what we have seen in the case of boundary conditions in electric fields. Now, this is B1T, where B1 stands for the component of the component along tangential for magnetic flux density, and this is B1N, again the magnetic flux density component along the normal, and this is B2T and this is B2N, that is the tangential and normal components in medium 2 of magnetic flux density. Now, there is a relationship between the components. The normal component is B1 cos theta 1 and the normal component in medium 2 is B2 cos theta 2 from the right angle triangle which we have seen of this sort, right? Because this is theta and this is the normal component and this is the tangential component and this is the magnetic flux density. So the normal component is always equals to B cos theta and tangential component is always equals to B sin theta. So from that expression, these relations follow. Not just that, we can also write that H1T is equals to H1 sin theta 1 and H1N equals to H1 cos theta 1. Right? So these similar expressions can be written for magnetic field intensities as well. Right. Now, to discuss the boundary conditions, the aim is to determine B2T and B2N or H2T and H2N if the values of B1T and B1N or H1T and H1N are given. So this is pretty much the aim of the boundary conditions which we have discussed in the case of boundary conditions in electric field problems as well. And we have obtained two equations, that is the closed surface integral of B bar over a surface body is equal to 0 because magnetic monopoles does not exist. Right? If the same expression is written in case of magnetic field, this still apply because B bar is nothing but mu H bar, where mu bar is a constant. Similarly, the circulation of magnetic field intensity over a closed path is equal to the current enclosed by the path. This is our Ampere circuit law. And when this Ampere circuit law is written in terms of the magnetic flux density, from this expression, I would get that the closed path integral of magnetic flux density over a closed path is equal to the current enclosed divided by the permeability. Now that I have obtained these expressions, I also should define two bodies, right? A closed path and a closed surface. We use the similar closed path and closed surface we discussed. The closed path is a rectangular path which is having four different paths, and this rectangle is constructed with height delta h and width delta w, and these are the four different paths I have. And whereas the closed surface is a cylindrical, hollow cylindrical surface whose delta h is the height and it tends to 0, that is a very small height, and the cross sectional area of the surface which we have considered is delta s. Now that we have all the required parameters to solve these equations, let us go and actually solve these expressions. So this is if I overlap my entire problem on the closed path, this is what I would be getting, right? In order to circulate, now I would have to calculate the in order to calculate integral of h bar dot dl bar, what I would be doing is, there are four paths. I would be splitting this into integral of h bar dot dl 1 bar plus integral of h bar dot dl 2 bar plus integral of h bar dot dl 3 bar plus integral of h bar dot dl 4 bar. So this is pretty much similar to what we have seen in the solving integral of E bar dot dl bar equals to 0. Now for the first case, the answer is the H1T is from left to right, whereas dl1 bar is from right to left. So that is equals to magnitude of H1T times delta W, right? That is from the first component. Similarly, from the second component, it is made of two different paths, that is from H1n and H2n in two different, and the same thing but in the opposite directions of H2n and H1n here. So these two cancel out, and we would not be getting any normal component out of this. And for the third path, H2T and dl3 bar both are in the same direction, so that is H3T times delta W. This is to be equals to current enclosed by the path. So I'll rewrite those, everything what I have said. The closed path integral h bar dot dl bar can be written as sum of four open path integrals, h bar dot dl1 bar, h bar dot dl2 bar, h bar dot dl3 bar, and h bar dot dl4 bar. Whereas on expanding those terms, this is what I am getting: minus h1t times delta w plus h1n times delta h by 2, because this second path has two components, half from h1n and half from h2n, right? Similarly, the fourth path has the other half from h1n and the other half from h2n. So these two anyway would cancel out. What I'm left off is from the first path and the third path. See, for detailed explanation, please visit the boundary conditions on electric fields, right? So that was there. I have given you a more detailed explanation. Here I'm just moving quickly because this is something which we have already seen. So final expression would be H2T times delta W minus h1t times delta W. That is the left hand side of the Ampere circuit law. The right hand says that this is equals to the current enclosed by the closed path. So the current enclosed by the closed path is the linear current density times delta W, because we are discussing about the interface. So the current enclosed would be delta W times the K. But if we assume that at the interface we don't have any free current, then this K would be equals to 0. Because the K equals to 0, then I can write that H1t is equals to H2t. That is, the tangential components are equal. Please understand that this is only possible if the interface is free of any current. If it is not so, then the difference between the magnetic field intensities, the tangential components of the magnetic field intensities, would be equal to the linear current density at the interface. But if it is not having any current, then they are equal. The difference is 0. So now applying the trigonometric ratios, I can say that h1 sin theta 1 is equals to h2 sin theta 2, or otherwise in terms of magnetic flux density, b1 by mu 1 sin theta 1 is equals to b2 by mu 2 sin theta 2. Now for applying the Gauss's law for magnetic fields, the Gauss's law for magnetic fields says that because magnetic monopoles does not exist, then the closed surface integral of b bar is equals to 0. Now this closed surface integral means the number of magnetic flux lines leaving the surface. In the medium 1, the magnetic flux density is entering, and in medium 2, the magnetic flux density is leaving. The number of magnetic flux lines entering through medium 1 is equals to b1n times delta S, and number of magnetic flux lines leaving through medium 2 is b2n delta S. If they are supposed to be 0, that means b1n should be equals to b2n, right? Because delta H is assumed to be 0, we say that there is no magnetic movement or no magnetic flux movement across the curved surface area. Whatever is that, that is over the flat surface area, right? So integral of b bar dot ds bar is equals to 0, whereas integral of b bar dot ds bar can be written as minus b1n delta s plus b2n delta s. And if these are supposed to be 0 for all the surfaces, then b1n should be equals to b2n. That is, the normal components of magnetic flux density are equal. That is, b1 cos theta 1 is equals to b2 cos theta 2. In terms of magnetic field intensities, mu1 h1 cos theta 1 is equals to mu2 h2 cos theta 2. Now, if I divide equation 1 with equation 2, then I can say that tan theta 1 by tan theta 2 is equals to mu1 by mu2. We have obtained a similar relation even in terms of electric field intensities also, and epsilon 1 and epsilon 2. Right? So this is again, this analysis would be used in solving some problems of EMT, whereas the previous results till here, we would be needing them to determine the magnetic field intensities for medium 2 if magnetic field intensities for medium 1 are known. Thank you for your attention. If you have any queries, please ask in the comment section.